computational approach for the no-core shell model. But to start with, I thought it might be interesting to go over some discussion of symmetries. This builds very much on what you've seen in some of the previous lectures, so we'll go relatively quickly through it. But of how symmetries are entering into nuclei, and also, I know you've been getting a somewhat piecemeal introduction to angular momentum algebra, spherical tensors, and how that rotational symmetry is used as then an analogy as a starting point for higher symmetries. So there are a few slides which might pull that together a little bit as well. So there are symmetries of the fundamental interactions. Those may be important for deriving the nucleon-nucleon interaction, but are not so much what we're discussing in nuclear structure physics. There are the symmetries of the shell model fermionic degrees of freedom. You will mostly be getting this from Pete on Monday. Well, you've seen isospin a little bit. You'll be seeing SU3 symmetry. So things are a little bit out of order here. You'll be getting the application of SU3 symmetry to ab initio calculations before you get SU3 symmetry. But then and then also an extension, the so-called symplectic symmetry. There are also symmetries related to pairing degrees of freedom, which Augusto Machiavelli might touch on a little bit. I'm not so sure about that.
I will discuss pairing.
Oh, okay, that's right, okay. So like pairing of a single type of nucleon is an SU, you have an SU2 quasi-spin symmetry again. For pairings of protons and neutrons simultaneously, you get an SO5 symmetry. This little picture is showing it's a diagram. Oh, this is exactly what I started sketching on the board the other day. Diagram of the states that would be included in an SO5 irreducible representation according to some labeling scheme. Okay, it's a pretty picture. That's the extent of it for now. And then you also have these symmetries, though, in the collective models. You've been getting a lot of U6 symmetry this week. The calculational method that, if you had gotten to problem 3 of Monday's exercises, you would have been using is the algebraic collective model, which involves some symmetries as well. All except maybe this last one here are, so a lot of these, okay, let me rephrase that. There are two approaches to using symmetries in physics. One is to get an exact solution to an approximate problem. So for instance, the IBM approach you've been seeing says, let's approximate our system as a system of S and D bosons, and then that system we have some exact solutions to. There's the other approach, which is to try to use the symmetries to help you with getting the approximate solutions, the grind away and try to get the solutions subject to certain computational limitations, but of the exact original problem. That's more the spirit of, I guess, some of the shell model symmetries. But here the idea is we're using symmetry as a computational tool, something to help us with that process of that generic process we have. Build your model space. Write the Hamiltonian in terms of as it acts on that model space and diagonalize. And you're dealing with this issue of truncation. Maybe you can get some help in the truncation scheme as well by using these, making use of symmetries. You've been hearing about Lie algebras a lot. This is the formal definition of a Lie algebra. So it is, right, I think it's probably been left as sort of fuzzy so far. It is nothing more than a vector space. I'm hoping you've all had linear algebra. I won't make you raise your hands. I know some people somehow bypass linear algebra. If you have bypassed linear algebra, go back, sneak into an undergraduate linear algebra course, put on a disguise or something, and it's really useful to clear up the definitions of what's a basis, what's a vector space, and so on and so forth. So I won't go back and, well, except a brief definition. A vector space is a set of objects, they're called the vectors, with an addition and a multiplication by scalars. And the key things are that we have closure. Add two vectors, you get another vector. Multiply a vector by a scalar, you get another vector. And then we have a linearity property. Basically, multiplication and addition have a distributive law. So that's a vector space. And then there is one extra thing that turns a vector space into a Lie algebra. In addition to multiplication by a scalar and addition of vectors, you also have a product of vectors of sorts, indicated by this bracket. That's very suggestive of a commutator. And that product has to have closure. Take two vectors and get their product and get a new vector. You have to have a linearity property with respect to addition. This product has to be anti-symmetric, anti-commuting, and it has to obey the Jacobi identity, which is exactly the identity that the commutator satisfies. You can crunch it out and verify that at some point. So that's actually why we care about the algebras in physics for the most part, because we have operators that can obey commutator relations. You actually all saw a Lie algebra in introductory physics without even realizing it. Right? The unit vectors in three-dimensional space have the cross under the cross product. Obey the, so vectors in three-dimensional space under the cross product obey this. But okay, we had a question. Someone had a question. Okay. But in quantum mechanics, we have, okay, so what was this pointing out? Oh, matter of definition here. A vector space spanned by d basis vectors. That's the whole idea. You can get all all vectors is a linear combination of a set of basis vectors. The number of basis vectors you need is the dimension. All right, so now why should we care about Lie algebras in these quantum mechanics applications? Well, there are Lie algebras hidden inside our quantum mechanics problems, and we have to realize that there are two vector spaces involved. We have a space of states, that's our Hilbert space. That's what we normally think of as the vector space involved in our problem. But we also have a space of operators. We have a rule for what it means to add two operators. The result is the sum of the results of the individual operators. We have a rule for multiplying an operator by a scalar. And then we also have a product operation, the commutator of the two operators, which you can verify is indeed a Lie product. Example, angular momentum algebra. We have the operators jx, jy, and jz. Sure enough, they are closed. Rather, their span is closed under the operation of commutation. There's another interpretation of the algebra, which is as the generators for continuous transformations. This idea is we also can take an exponential of an operator, and that turns any Lie algebra, when you take the exponentials of the members, that gives you the members of a Lie group. A ton of theory there, which we won't go into. The example, you get the rotation operators as a set of exponentials of members of our SU2 space that is linear combinations of the J operators. That's the math side. The physics side, then, is we have symmetries, which are then variants of the Hamiltonian under some transformation. Those transformations are the members of the groups, and working backwards, we're then interested in the algebra, the generators of the transformation. So rotational invariance is why we're interested in the algebra of angular momentum operators. So the invariance under the group means that the Hamiltonian commutes with the operators in the algebra. And then you know the whole game that comes from that. The eigenvalues of the Hamiltonian are then formed degenerate multiplets with respect to the groups, the algebra laddering operations. And those different eigenstates within that multiplet are related. They basically can be rotated into each other. The angular momentum degenerate states, the different magnetic substates, are related, at least each one is rotating one of them gives you some linear combination of the others, according to those D functions, which we saw the other day. That's, in a nutshell, what we get out of group symmetry. This idea of angular momentum multiplet generalizes into the idea of an irreducible representation of more general groups. So think generalized multiplet when we say irrep. Irrep is the in-group shorthand for irreducible representation. So if you want to be really cool, call them irreps. Okay, so on a practical side, what we get more than just a grouping of our eigenstates into irreps. We get some computational benefits out of that. Let's again take SU2 or SO3 as our example. Those are again, angular momentum. We have the laddering operators, a particular combination. So we have two types of operators in our space of operators. We can group them into laddering operators, which raises or lowers some quantum number, some label of states within the multiplet. And then we have what would more generally be called a weight operator. It's something that weighs a state, you can think of it as. It measures how heavy it is, what its value is for some label. Are you at the bottom of the multiplet or the top? So everything about the multiplets follows from these commutators. The laddering operators, because of their different commutators, with the weight operators, move us around in the multiplet. J0, if you measure with J0 before, as opposed to after acting with J plus, you'll get a +1 difference, and that's due to this plus sign, this commutator. Before or after acting with J minus gives you a minus sign difference. It lowers M by 1. And then we have this closure relation here, this remaining commutator, and it was from these commutators that everything else was derived when you derived angular momentum algebra. All the matrix elements of the basis operators, which I'm going to lapse into calling generators occasionally. So the matrix elements of the generators were derived from the commutator. And then, okay, this is the point that our states form an irreducible representation connected by ladder operators. This whole representation has, what's the difference between different angular momentum representations? It's basically how many states they include. If you say a multiplet has angular momentum 2, that means that the weights that are enclosed were everything from +2 to -2. So when we're talking about angular momentum 2, we have all this, we probably come to it with all this baggage in terms of classical angular momentum vectors and lengths of arrows and things like that. But from an algebra point of view, angular momentum 2 means that the highest weight in the irrep is m equals +2. End of story. Everything else follows from these properties. I say that because when we go to higher groups, that's how we'll label our irreps. What's the highest weight state or the lowest weight state in the works in the irrep? Those are the irreps. We also have now this concept of tensor operators, which is where the real mathematical, practical power comes in. Yeah, just grouping our states doesn't help us unless we actually gain something from doing that grouping. And so there are a couple of things to bear in mind here. One, actually, before we get to tensor operators, is at the level of states. If you have two different subsystems, say two particles, and you take you'd have their product states, you can find a certain linear combination, and those coefficients are the coupling coefficients, or Clebsch-Gordan coefficients, that will give you members of a new angular momentum multiplet involving that two-particle system. Now, on the other hand, we have spherical tensor operators. Those are defined by the fact that the way you recognize a spherical tensor operator is that under rotation, and remember that to rotate an operator, you sandwich it in your rotation operator. The new operator you get by rotation is a linear combination of so it's actually a misnomer to talk about a spherical tensor operator. Really, the spherical tensor is a set of operators labeled by an m quantum number. So it's within that set. If you rotate one member of that set, you'll get a linear combination of other members governed by those exact same d coefficients that rotated states. And we care about this because most interesting operators for us are spherical tensors. The coordinate operator, x, is, so anything that's a vector in our traditional terminology is a rank 1 tensor. Then things like the spherical harmonics are tensors, the electromagnetic multiple operators are tensors, shell model creation operators for a particle in orbital J are spherical tensors of rank J. So we have lots of tensors operators floating around. Then finally, to tie this together, we have the Wigner-Eckhart theorem, which says if you have a pair of states of good angular momentum and a spherical tensor operator, then all the different matrix elements among all the different members labeled by different m's of those irreps, connected by the different corresponding m's of that spherical tensor set of operators, all the dependence on the m's just follows a Clebsch-Gordon coefficient, and we're just left with one normalization constant left over. Now, this is what we've been saying repeatedly, actually, but never quite drawing out properly. Proportionality constant, you could pull any m-independent factor out and make it a conventional prefactor. So, in fact, because of some of the Clebsch-Gordon symmetry properties, it's common to pull out a factor of 1 over 2j3 plus 1. That makes the reduced matrix elements a little bit nicer. You'll see a note in the exercises today. It makes the magnitude independent of which you take as the bra and which you take as the cat. So that's the convention used by various authors. Edmonds, is the most common one. I think in Pete's notes, he left off this factor. That would mean that he was using the phase back, the convention that was used in the standard textbook by Rose. So there actually are some other slightly different conventions floating around there. Sort of, how many of you have seen the book by Edmonds? It's a little pamphlet. Princeton University Press is the new edition. It has pages which just try to correlate the phase and normalization conventions and notations of different authors. It's actually depressing when you look at it. But at least we're down to pretty much 2 or 3 standard conventions these days. Okay, so between two multiplets, irreducible representations, all matrix elements follow from one reduced matrix element and from coupling coefficients. So notice there's 2 completely different uses of coupling coefficients. One is to couple different states to get a new state with good symmetry, and the other is to couple states to operators, basically, to get different matrix elements. This is powerful for an angular momentum algebra, for the angular momentum algebra. The same game can be played, though, with more generalized groups. So we'll have to think by analogy, and I won't be going into, I guess, the concrete details of it all. But you have things like SU3 labels, SU3 Clebsch-Gordon coefficients that can be used to deduce matrix elements. Okay, so actually on this sort of more abstract formulation of it, any questions, thoughts?
Yeah. About the convention of the phase of Wigner-Eckhart, which one we should use?
For today's exercises, because, right, so the matrix element is a concrete thing. There is no, well, there are choices of phase there too, but this is sort of the real thing within some phases. This, though, is just within saying, here we have an M dependence and we can pull out conventional prefactors. And so that's where we have complete flexibility. Most nuclear physicists, no, that's not even true. So, right, there are 2 sort of standard textbooks, Eisenberg and Greiner, Bohr and Modelson, and as you might guess, they use the 2 different phase conventions. Right, if there are 2 textbooks, they'll have to use 2 different phase conventions. So, right, both are widely used and accepted. I started out using Rose, and I ended up switching pretty consistently to Edmonds. I think a lot of I'd say most maybe the shell model work uses Edmonds. If you look at Suhonen, it uses Edmonds as convention. The books by Rowe use Edmonds as convention. Probably if you're picking a choice, Edmonds might be the safer one, and certainly for today you'd use that. But someone else might say, are you crazy? Why don't you use the other? There are group theoretical, Rose's generalizes more nicely to higher groups where you don't necessarily have such a convenient factor to pull out. So I think that's the motivation there. Edmonds just makes the normalization of this guy convenient. Varshalovich, that big, impressive angular momentum reference that Pete pointed out, also.
It's over there. The book is over there.
Yes. This book and this book both side with Edmonds, for whatever that's worth. Okay. So SU3 in a nutshell, I know this will be a little bit abstract till you get the details more from Pete on Monday. These are groups of operators which Elliot, in the 50s, realized could incorporate deformation and rotational correlations into the shell model. Traditionally, this was just working in the valence shell, and then it was expanded. And practically now, the hope is that in the no-core shell model, the dimension needed, and there actually have now been calculations done doing this, the dimension needed for convergence can be reduced by saying, okay, we have some correlation that we know is going on in the nucleus. We have a way of building it in advance into our basis. There's no fundamental limitation here. It turns out you can classify all the no-core shell model states according to SU3 symmetry. So in the end, you can recover the full no-core shell model, but you can try cutting some of it away based on SU3 symmetry, get a smaller problem at hopefully the same level of numerical accuracy. SU3 then, so what are the generators of SU3? It's the angular momentum operator, which can be written, though, in a form that might seem a little bit unfamiliar. I should probably be a little bit more explicit here. What we're saying is sum over all particles in the nucleus and act on each particle. So this is a one-body operator with the phonon, the oscillator quantum creation operator twice. So hitting each one particle, it would basically, sorry, with the creation operator, then annihilation operator. So it takes a particle, raises it one shell, and then brings it back down into another substate of the same shell. You can write the angular momentum operator in that form when you're working in an oscillator basis. And you can also write the quadrupole operator in that form when you're working in an oscillator basis. So it's specifically within, so those two operators, it turns out, are closed under commutation, so you get a group structure coming out. Another way of looking at this is that a single particle in an oscillator shell has definite SU3 symmetry under those operators, and there's some labeling scheme. So basically, an operator in the like here, an operator in the 0, 1, 2, 3, n equals 3 oscillator shell turns out to be its substates. So if you consider all possible substates of a major shell, those together form one irreducible representation of SU3. You can connect all of them by some combination of those operators. And the label for that URF is just, in this case, 3, 0. So if one particle has good SU3, you can then imagine coupling together many particles to get good SU3 for the many particle system. So what do we get out of SU3? Well, this is the symmetry introduced by quadrupole-to-quadrupole-quadrupole interaction. That's a schematic interaction, but it gives good many body states with good SU3. Those states in an SU3 IREP share the same deformation because basically the quadrupole moment, one of the generators is the quadrupole operator, so it turns out the quadrupole moment is conserved within an IREP. And also when you look at the spectra that come out from Q.Q Hamiltonian, you get rotational bands, rotational spectra. So that was the classic view, and then the idea now is that you can try to build this in as a coupling scheme to the no-core shell model. And as of a couple of years ago, there's now the Louisiana State no-core shell model code, which works in this scheme. That's one step. You can build further, and this was proposed by David Rowe and by Rosenstiel in the early 80s, which was SU3 is part of a larger group that's involved if you take not just the phonon oscillator creation and annihilation operators paired with each other, but you also take the pairs of two creation operators or two annihilation operators Or also, there's one extra operator here. This is just the number oscillator for oscillator quanta. Throw those in, and so what does that do? That would be situations, say, where you take one nucleon and promote it up by 2 shells. So this clearly then is moving out of the valence shell. This only makes sense in a no-core shell model type picture, a multi-shell picture. And this still builds in a lot of SU3 properties, but it also has some special properties, like the kinetic energy operator. Basically, kinetic energy operator is momentum squared. These phonon operators can be rewritten as combinations of coordinate and momentum. So you can imagine that when you take the product of 2 of them, you get p squared terms, x squared, and so on. P squared by itself does lie within this space. So you basically have the kinetic energy lying within your algebra. So that means the kinetic energy will conserve the quantum numbers here. So you can build states that already have the kinetic energy that won't be mixed by the kinetic energy. So there are some other arguments for a symplectic approach. So the idea is beyond SU3, we want to build up into the idea of perhaps using symplectic symmetry to pre-construct many body states which are already going to be close to the nuclear eigen states. That's the next step. But to present the general schematic here, SU3 generators move a single particle within a shell. sp3r generators can also promote particles up by 2 shells at a time. SU3 IREPs have definite deformation. These are the 2. So an SU3 IREP in general is labeled by 2 quantum numbers, lambda and mu, which, without going into detail, they basically tell us what the highest weight state within the IREP is. Once you look in the you have to build up all the laddering operators. You realize the quadrupole operator can move you around. You have ways of assigning weights to states. So there's a lot of machinery there, which we won't go into. But okay, so you have definite deformation for those states. And then sp3r, if we apply this to no-core shell model, basically would take you up in steps of 2 in your excitation quantum number. So if you start with an nmax 0 state, it would give you some subset of the nmax 2 states, nmax 4 states, ones that are closely related and could be related by the kinetic energy operator, for instance, to those lower states. Or you can start with an n equals 2 state already and then use symplectic raising operators to get you up to higher states. So a natural way of selectively building a no-core shell model basis with high excitation quantum numbers. So, for instance, although we might never be able to get to n equals 30 to get our Hoyle state to converge by a brute force approach, we might be able to get the important states up to n max equals 30 by this much more selective approach. Yeah, a lot of that still is under development, but SU3 part is very much active now. So to give you an idea of some of the results that have come out of that, let's look at lithium-6 first, not particularly a rotational nucleus. We'll finish up by looking at a rotational nucleus. Right, so let's see. This code builds no-core shell model space of states with good SU3 and also good spin quantum numbers. So if you look at your model space, this shows the different subspaces, but I'm not expecting you to read these numbers. These are different SU3 labels, like those Elliott labels, lambdas and mu's. These are the different spins, so total spin for the protons, let's say coupling of 3 halves and 3 halves for the neutrons and 1 for the combination would be that example. You can break your space up this way. This doesn't look too bad. You say, oh, we're saying that no-core shell model space explodes. I don't see this exploding until you realize that these radii are on a logarithmic scale. So this space is, at the very least, thousands of states, whereas this space is 1 state. So things are growing a lot.
What is this thing? It looks like the old things that you do in the computer. But
So our nickname for them is punch card plots. Yes.
what is that thing? I don't understand what this is.
So, okay. So this is saying we have our basis for the space.
Okay.
We can break our basis down into subspaces subbases with definite SU3 quantum numbers and spin quantum numbers.
Somehow with these chains or?
With these, yeah. So we can come back later and I can sort of give an idea of how you go about constructing them. Naively, you could say, well, think for instance when you did the, talk about the shell model a little bit earlier this week, you had individual particles and then you coupled them up to get states of definite J. Like you had a 3-particle system and you did some intermediate coupling and you got us with coefficients of fractional parentage and you got a state with definite J. We can do the same thing here and get some states with definite SU3 quantum number 14, 1, or some with, I mean I can't even read these on the scale, but some with SU3 quantum numbers 10, 1, and so on. So we can build our basis but with good couplings along the way, and that gives us these different subspaces. Right here I'm just showing this circle's size represents 1,000, let's say. That means we were able to build 1,000 different states with quantum numbers 12, 1. This one's size maybe represents 100 states. That means that we're able to represent, I should say this is at n equals 12 quantum excitation. This is at 10, 8, 6, 4, 2, and 0. So maybe it's easiest in our valence space. In our valence space, n max equals 0, we can build a bunch of states, a couple of states with 2, 0, certain SU3 quantum numbers, but only with angular momentum 1, or spin 1, but if we go to spin 0, we can build some states with different set of SU3 quantum numbers. So that sort of, it's a lot to digest. I know I'm skipping the actual construction process, but yes. Right. So that's actually one nice thing. You get good J scheme, so to speak, out of this as a free bonus.
But
yes.
Spin here is spin.
Oh yes, yes. So that's our wonderful nuclear physics sloppiness of sometimes using the word spin to refer to total angular momentum, and sometimes just to the intrinsic spins. So this is you essentially have an LS to J coupling scheme going on. SU3, notice all those operators, the L operator and the Q operator were written entirely in terms of we can go back and look, written entirely in terms of spatial coordinates, positions, and momenta. Nothing with spin was involved there. So SU3 is completely a symmetry of the spatial coordinate degrees of freedom, so orbital motion. It decouples basically from the couplings of the spin. So you get basically lambda mu, the SU3 quantum number. You can branch that out to definite orbital angular momentum, figuring out what spins go with that, and there are some constraints due to the Pauli principle, and then couple those two angular momenta to get the total angular momenta. So you have the LS scheme built in as part of this, basically. All right, so this is our space, but then if you look at, you do an actual diagonalization, this was with the GIS16 interaction, get the lithium-6 ground state, and look back at what amplitudes contributed, right? We're getting our state in some linear combination of all these states, but it turns out most of the coefficients are very close to 0, and we're dominated by basically the low total spin, that's the S, coupling. It's coupling basically to 0 or 1, and the so-called leading IREP, which if you look back here, is basically the largest deformation IREPs. There's some formula in terms of the lambda and mu labels. So you could say right away, well, maybe we could even do pretty well with our calculation if when we built our space, we didn't even bother with all these other SU3 IREPs, all these other spins, and just took these states. Obviously, that won't get us exactly to the answer. There are other contributions out here. You need a more systematic approach. But that's the basic idea going on. On the flip side, aside from computational efficiency, you have the idea of, well, exactly the question that came before, can you look at these ab initio states and read off some symmetries from them? And it looks like we're reading off SU3 symmetries here. There's another way of plotting exactly the same data that was on the punch card plot, which is to use a histogram here showing here are our n equals 0 states, so our valence space states. Here are the states with 2 oscillator quanta, 4 oscillator quanta, and so on. We know as you add more oscillator quanta, those contributions become smaller, so look at the scales here. 60% of the wave function comes out of just 0 h bar omega states, valence type states. Another 14% or so comes out of 2 oscillator quantum excitations. It's down to 10% or so for the next level, only 2% for 6 oscillator quanta. But within each of these levels, you can look at the different SU3 irreps that contribute. The so-called leading irrep, the most deformed one, is at the right, and you see a big contribution from that one, and then some subdominant contributions. And so this is where you can start to look, and at this point it is just starting to look, but it's pretty promising. Right. Look and see, well, are these the irreps that you get by acting with the symplectic generators? And there was actually a submodel of the symplectic model which predicted that you would always get states lying basically in the leading space. Yeah, there's a lot that still needs to be investigated here, but this is at least consistent with a symplectic picture built on top. So that's basically motivation to go further with the symplectic approach. But in any case, to answer the question from before, yeah, you're seeing SU3 symmetry popping out. Now that, in lithium-6, that was not a terribly rotational nucleus, but now let's look, this is all just actually the ground state. You can do the same thing with excited, do similar plots for excited states as well. But so let's look at the ground state of beryllium-8, which we saw as part of a rotational band. And again, you're seeing basically good, here already we have 50% of the wave function is from the valence space, and that is coming basically entirely from an SU3 4-0 symmetry. So yes, it's looking like SU3, but then what we have beyond traditional SU3 is we have these contributions from higher oscillator excitations, and those again have some sort of SU3 character, but this is a different irrep. This is 6-0 here rather than 4-0 going on. There are some subtleties like the distribution of particles among the shells depends also on what your oscillator length was. Think of it, if you're using an oscillator basis, the same state could either require just a few oscillator basis functions or many, depending how you chose your length parameter. That would show up as just requiring a few low quanta or some high quanta, depending. So there are a lot of subtle things which you have to be treated as you look more closely, but this is the basic idea. I think that is it. So just to try to summarize, what we have here is what looks like emergence of rotational patterns in ab initio calculations, more readily identified on or near the ERAS line we saw. Things get messier away from there. It's mostly we see it out of ratios, although M1s are converged enough that you can see things from absolute M1s. Plenty of open questions raised by this. Can we get quantitative prediction of the band properties? That's difficult because convergence rates vary depending on the observable and also depending on the band structure. We might, as things develop, be able to extrapolate more effectively to the full space results. What we haven't looked at here, though we've started to look at it elsewhere, is the dependence of the rotational properties on the interaction. Yeah, just 16 is just one interaction. And then that big question, seeing rotational separation is one thing. Can we figure out the nature of the intrinsic state? There are lots of traditional interpretations. The cluster structure interpretation, that the beryllium isotopes are 2 alpha particles plus some extra neutrons, say. Does valence structure come into play? It looks like it because that valence shell term and that valence angular momentum cutoff playing such an important role, but some of that may actually be reflecting just convergence rates rather than true structural effects there. Then there are the deformed shell model descriptions like the Nilsson model, which you'll learn about next week, and then this big one, which is the relation to Elliott SU3 and to symplectic rotation. So I think that is it for the formal part of the lecture. And then we have another 40 minutes or so that we can talk more informally about either the details of no-core shell model calculations. I know I have some questions at the break that we can go into, or whatever else comes up. And if we completely run out of things, you can start looking at the handout and get a head start on thinking about the exercises. And that's it for this.
Here's a question.
Oh yeah.
Why was important introduce the extension of the SU3, I mean, in terms of symplectic groups?
Basically, because of that issue, that the SU3, so there are two answers to that. If we restrict ourselves to the framework of SU3, there's the idea that the SU3 operators, let me go back to that, all conserve the number of oscillator quanta. Right. The key thing about SU3 is it's a B dagger with a B.
Okay.
So it can tell us about structure at a given level of oscillator excitation, typically just the valence shell, but it can't tell us so much about the relation between those different levels, those different contributions to the wave function. You cannot, for instance, use it to build basis states. You can't start from lower basis states and build a selected set of higher basis states using it because it doesn't bring you up to higher levels of oscillator excitation. In contrast, B dagger can bring you up to configurations with more oscillator quanta, two steps at a time. Yeah, that's it. From the SU3 perspective, that's the way of thinking about it. There's an entirely different perspective saying, forgetting about Elliott SU3, the kinetic energy is an important operator, angular momentum is an important operator. In all those mean field shell models, the number operator for the harmonic oscillator was basically our mean field Hamiltonian. So if you want an algebraic approach that encompasses the kinetic energy, which comes out of these guys, or the A's and the B's, and the harmonic oscillator Hamiltonian, then you need these blue guys, and if you want closure, then you have to throw in the red guys as well. And so you get SU3 coming along for the ride. So that's much more the approach of David Rowe's symplectic model, which has been applied to very heavy rotation, heavy nuclei as well. Yeah?
So I'm a little bit off the topic. I mean, for me, it was very hard to follow through this, but I think it's natural because it's the first time I see this stuff. I was wondering, so this goal of the whole lecture was somehow to show us that starting just from nucleon-nucleon interaction, you can somehow figure out collective properties.
Right. And that's some of the, the first goal.
So that means that these models that we have, the shell model, the IDA model, and the collective, the geometrical models are somehow really related in between. They're not just some different stuff that just people figure out.
So that would be the ultimate hope. Now, disclaimer, back where some of us were just talking about this over break. Disclaimer is rotation in beryllium 8 is very far from gamma vibration in 168 beryllium, for instance. So it would definitely be a long way to providing a foundation for all those models. But yeah, all those models, the hope would be, there are two choices. Either they really are supported by microscopy, or they're wrong. And the goal would be ultimately to try to figure out what aspects, none of them are even intended to apply all the time, so it's almost sort of a moot point. But the question is, what aspects of the physics that was assumed in those models actually can arise from an ab initio approach at some level? And the no-core shell model is, at least, maybe in the symplectic form, it would be able to start reaching that high. Certainly in the basic form, or some version of the symplectic model, you can actually be able to bridge those gaps. But for the basic no-core shell model, it's probably not going to get you terribly far past mass 20. So it may help you with pairing models in the light nuclei, but for instance, but it won't get as far as the geometric model in the heavy nuclei. Other questions before we switch modes?
Yeah. When you diagonalize your huge Hamiltonian, can you find the eigenvectors and perhaps map out the density?
Yes,
in sort of
and
clustering could
no.
emerge. Yeah.
So there are actually, I should have had that as an example slide, as a backup slide. So the answer is yes, and so actually the Green's function Monte Carlo people did something like that for beryllium 8, and then for beryllium 9 we actually have, Peter Maris has a paper out showing that, and yeah, it looks sort of like 2 alpha particles. There are some subtleties going on, like the problem is we are calculating the full state in the lab system. It never looks just like 2 alpha particles sitting there stationary in space. Those are convoluted with the whole rotational motion. So you have to be very careful about, classic example is, if you have a truly collective rotation, so you'd say 2 alpha particles, that's prolate, right? All in favor of that being a prolate shape? Raise your hand. This is a trick question, but you won't have to feel bad about it afterwards. Now, we also have the idea that an object cannot rotate about its symmetry axis, right? So which way would the rotation axis of this thing have to be pointing? I sort of gave that away with what I did with my hand, but not up and down, right? It would have to be pointing, well, anywhere in the plane. So let's look at something like this. What happens if you take a dumbbell like this and average it over rotation around in a circle like this?
Oblate.
You've gotten an oblate, you've gotten a donut. Take 2 alpha particles, sweep them around like this, and you create a donut.
But this is not the symmetry axis. I mean, if you rotate one to and this, you get the same axis or not?
Exactly. I'm not sure if I like that.
So the axis that you draw, it's not symmetry axis because it looks like mirror plane.
It will be no. So the so if you have the 2 alpha particles here,
Yes.
the symmetry axis is the vertical axis. If we rotate around it, we have the same thing. If we rotate in the board our alpha particles, this is not the same as this.
Yeah.
Okay. All right. So yeah, so you can select out a specific M substate and try to translate between the pictures, but it does start. The only thing that's really clean is if you just take a radial density distribution, since then you've already averaged overall rotation, and then you can see if a dip in the middle is suggestive of a 2 alpha particle structure, for instance. And then yes, you can play these games, but you have to be very careful about interpreting this. Okay. Other questions?
Are you looking for vibrations?
It's not continuous, it's C.
You mean like alpha molecular vibrational
You
modes?
have this volume state, for instance.
Yeah.
3 alphas, and you would
Yes,
imagine
yeah.
that there are.
When we get up to the carbons, I guess we start looking for things like that. Yeah. Okay.
I've got a question about the difference between the ab initio techniques and the other one. Because my point is, so the ab initio techniques start from QCD, then build up a nuclear-nuclear interaction. But after that, from what I've understood, the treatment is more or less the same, meaning that you're using a no-torsional model. And that could be used as well, as far as I understood, without using a nuclear-nuclear interaction derived from QCD. Could be like, it's just a matter of the potential you're using, right?
So I think your point here is that ab initio refers to the entire chain of starting from, well, it depends where you consider the beginning to be.
Yeah.
Right, if your beginning is the interaction, then going to the nuclear, this step then would be ab initio. But if your beginning is actually QCD, then you would need this full link. And everybody knows that quarks aren't really the fundamental degrees of freedom, and to be at truly ab initio, you probably have to start at the grand unified theory scale or something. But yeah, so it's all relative. But at least, I would argue that yes, to be ab initio, you need, right, in which we don't actually have, we do not have a fully derived from QCD Hamiltonian now. Right now we have forms that are coming out of chiral effective field theory. There's work on the lattice, but it's not yet the stage of giving us the full. So this is really more a program that, this is not something that is accomplished fully yet.
But to go on with discussion, so what you get from this lattice QCD works is the nuclear-nuclear interaction, which gives you the potential in the Hamiltonian.
Yes,
Is that correct?
that's right.
Okay, and then you make a more classical treatment from a nuclear point of view, which is making a shell model with no core shell model.
But that's why the claim is that it's not that no. In fact, that's why we're trying to move away from the term no core shell model. It's no core configuration interaction, meaning you're building your space out of Slater determinants of product spaces. But if you bring that truncation to infinity, you've built the whole shell model, the whole space for the 8-particle system. So yes, there are these issues. If you truncate at n-max equals 0, you do just have the shell model. You have to then carry out that step of building up your, untruncating your space, if you will, to get, right, we're just using this as solution in a basis. Maybe I'm not saying
No, maybe
answering
I
to the
missed
question.
something. My question is more like, from what I understood, all the point is that you're starting from this QCD and get the nuclear potential, and then use it in a framework which has only been used, as far as I understood, or am I missing something? My point is, what I'm surprised about is that you obtain some interesting results showing that you have rotor behavior in the light nuclei, and I was wondering why that would have been shown, why you could show that with your nuclear potential, and that hasn't been shown already with a more classical potential. Or am I?
I mean,
maybe because
right.
I
See.
But my impression is that you're doing something which has already been done with a different potential, and that's
Right. So if you start so rotation in the P shell, for instance, valence shell, is a decades old story. Arguably there, though, you're taking the phenomenology of nuclei, saying, we see these states, you fit an interaction to that, and you say, after we've done our fitting, we still see these states. That's shortchanging it slightly, but yeah. Right, it's still a lot has been put in by hand in that case. Yes?
When you have these situations of trying to predict observables with the core shell model, is there any effort in or point to comparing it to the Greenspan between Monte Carlo situation or the coupled core or
Couple cluster.
That would allow you to be able to say something deeper about the physics of where they come from?
Yeah. So and the question is, by comparing these different methods, can you get some insight into where the convergence failures, in some sense, are coming from? Probably, at least obliquely answering that, some of these extrapolation methods are being tried out simultaneously on coupled cluster and no core shell model. Definitely, if you saw synthetic conversion much more rapidly in one basis than another, you'd be able to, or one method than another, you'd be able to start comparing and say, what does one approach build in easily in terms of correlations that maybe the other one doesn't? That is a great idea, and actually, I think that's I almost echo it in the final paragraph of the preprint. So you can hunt for it and see there's a similar comment. But in practice, I don't have a concrete example of where that has actually turned up. Something concrete. That's a nice idea.
How do you extract the matrix elements that you need so you can, how do you extract the matrix elements of interactions from scattering? For example, you want to measure beryllium-8. What do you scatter on what so you can get the matrix elements?
Okay. And I profess great ignorance on the technical details of this, but it is nucleon-nucleon scattering. It's purely the two-particle scattering. So proton-proton, you can do proton-neutron, you can the problem with neutrons is, as we pointed out, they're uncharged, at least when experimentalists deal with them. So there's no real way of just trapping a neutron and scattering a proton off it. You can do it indirectly, like if you have a deuteron, that's a proton plus a neutron, so half your target is neutrons. Neutron-neutron scattering is basically not terribly doable. So you have this limited set, you have this very complete set of information from proton-proton scattering, somewhat from proton-neutron, and I believe not much from neutron-neutron. So that's the scattering input. You can revert, so if we have isospin symmetry, though actually all you really need is some subset of that data. You don't really need neutron-neutron since that should be partnered to proton-proton. But that's an assumption and somewhat of an approximation. Yeah, you can invert that to get a potential, but that is not a unique prescription. Just scattering doesn't, there are many potentials that can give the same scattering phase shifts. So what is then done is, here's where I hope I'm not saying anything too wrong out of my ignorance. If you're curious afterwards, I can point you towards a paper. Actually, in the preprint, everything is, that preprint is at least like within 3 degrees of connection or something of every other paper in the universe, maybe. There is, where I introduced the term JISP16, there is a reference to a paper by Shirokov, which is actually the paper where this whole procedure is spelled out. You basically then choose some natural form for the potential, and then you have some phase natural variations you can do to it which preserve the phase shift. So any of those varieties would be consistent with the scattering, but they change the many-body structure. So you try to fit that to a few basic things that can be calculated very precisely in the many-body calculation, like the helium-4 ground state we saw was nice and converged. It still is a pretty basic thing involving just a few particles. That allows you, and some of the other ground state energies in the light nuclei, allows you to fix those phase shifts given the limited number of degrees of freedom you've allowed yourself. So yes, there is still freedom there, and that shows up as you go to the heavier nuclei. Things start deteriorating a little, and maybe you need to refit those phase shifts a little. So that is, yeah, differing. It doesn't claim to be fully ab initio. In the other approaches, in the chiral QCD, chiral effective field theory approaches, you try to constrain yourself much more by the QCD properties. So again, you're fitting the nucleon-nucleon scattering for the two-body part, and then all your remaining terms have just a few free parameters that come out of the field theory. So you have very definite, and then you fit those again to a few basic quantities, and you're more or less locked in. So I think that probably more than answers the question, or excessively answers it, but okay. All right, let's take a 5-minute break, or just a pause, and then we can continue with a less formal interaction. Okay, yes.
Last question.
Yeah.
When I think about the E2, the M1, they're electrostatic or magnetic moments of gamma. And in my head, gamma decay is the interaction of the nucleus with its own electromagnetic field.
Or with the ambient electromagnetic field or whatever, yeah. Okay.
Sure. But the E2 matrix element, you say, has the tensor neutron part that's separate from the tensor proton part. And so
I'm saying that if we were predicting electromagnetic decays, it's only the proton part that contributes. There is the total quadrupole tensor. So, yeah.
What did you say?
So this operator here is what you would use to actually calculate electromagnetic transitions. Just the protons, because indeed it's just the protons that couple with electromagnetic field. So if you do perturbation theory, you say, oh, the electromagnetic field is tickled by those protons being there, and that's what causes a gamma ray to come off. However, this operator here was the, in a way, my way of writing this here was sort of governed by analogy to the magnetic operator, so we should be a little bit careful, I guess. This operator right here is a so-called mass quadrupole tensor. That would be measuring the overall deformation, but it's not what the electromagnetic field feels. I mean, it's measuring, right, it's a property of the nucleus. If you could stare at the nucleus with a microscope or probe it in something that feels the whole mass distribution, this is what would, this is like for mechanics. The inertia tensor in mechanics, as this nucleus is tumbling over itself, that the protons and neutrons are basically the same mass. So if you were talking about the moment of inertia, the nucleus is the top guy that matters, but indeed the electromagnetic field only feels the lower operator. And then the idea is if we're doing rotational analysis and if we want to see, we're looking for hints of rotational structure to the wave function. We can't actually look at it and see, I see a little d function written there and a little intrinsic state written there. We are at this stage at least working with indirect evidence, and we want to collect as much as we can. And there, seeing if this operator follows the Alaga rules is as perfectly good indirect evidence of a rotational wave function as this operator, because we're looking at the structure of the wave function. We're not trying to predict a gamma ray. That's even more extreme down here with the magnetic moments. If, yes, we're trying to predict the production of magnetic dipole gamma rays, then yes, we would have to make sure that the neutron spin is weighted minus 3.8 times the proton spin, or whatever that ratio would be. But, of course, for ab initio prediction purposes, yes, we want to be able to predict dipole transitions. But for investigating rotational structure through indirect measures, any one of these operators is perfectly good an operator for studying Alaga rules, and it focuses on different parts of the wave function in ways that I wish I fully understood. Okay, let's officially end this, take at least 15 minutes of rest, and then we can decide what we're doing next. So, 10.
But if you take 15 minutes back,
Did I say 15 minutes? That means my brain is fried. 15 seconds,